Okay, so let's take a look at section 5.4, the fundamental theorem of calculus. This is probably one of the biggest ideas in the entire course because it combines what we know about areas and indefinite integrals, but it also goes a little bit further later on in the section where we look at the connection between differentiation and integration. So make sure that you really master the concepts that you see in these videos, in these notes. Okay, so what do we know so far? Well, we know that the net area bounded by a function in the x-axis between x equals a and x equals b is equal to this limit definition right here. And we saw back in 5.2 that that was a really difficult process to kind of go through and use this limit definition to find the net area. We also saw in 5.3 that this was another way that we can write that net area equation, and we can also condense it down into this really nice, neat integral notation where we say that the net area bounded by a function in the x-axis between x equals a and x equals b is the definite integral of f of x between a and b. And in this section, we find that there is actually a really convenient way of evaluating this that is much, much more efficient than going through this complex limit definition process like we did before. Now to find net areas, when we're doing the definite integral of a function from a to b, looks like my a got cut off there, what we're going to do is we're going to take the antiderivative of this function, that's what capital F is, we'll plug in the upper limit of integration and then subtract what the that antiderivative function is when it's evaluated at the lower limit of integration. And so this is the primary result that we take away from the fundamental theorem of calculus, and you're going to be using this a ton in this class the rest of the way, but also this is really your foundation for Calc 2. So I'm not going to get into a complex proof right now in this video, but I do want to give you an example that just allows you to at least see that this works. And so take a look at this picture where this is illustrating the velocity of an object that's moving in a single direction. And so actually think of this over here along this line segment. Think of this as the path of the object. So our object is just moving along this line segment, and this is just the relationship between the velocity and time of that object. So we can see that for the first 2 seconds, our object is traveling at 4 feet per second. And so as a result, I've written in here 8. That means if you've gone 4 feet per second for 2 seconds, doesn't that mean that you've traveled 8 feet? So at time 2, our object's position is 8. Between time 2 and time 8, our object is traveling 8 feet per second. So if you go 8 feet per second for 6 seconds, then you are traveling an additional 48 feet. So our object has now traveled from position 8 to position 56, because from time 2 to time 8, we've traveled an additional 48 feet. So if you added 48 to 8, we're now at a position of 56. But now, between time 8 and time 10, our object is traveling negative 2 feet per second. So that means that the object changed direction, and it's going back to where we, the direction from where we started. And so if you've gone negative 2 feet per second for 2 seconds, then you've traveled 4 feet back in the original direction. That means at time 10, our overall position is 52 feet. Okay, so let's see what we actually have here. We can kind of summarize what we just did with this by writing the following. We can say that the integral of our velocity function from time 0 to time 10, we know is the net area bounded by this function and the x-axis. And so that would be 8 plus 48 and then minus 4, because this area is below the x-axis. So the net area bounded by the velocity function and the x-axis between time 0 and time 10 ends up being 52. But 52 is the same thing as the position at time 10, as you see right here, minus the position at time 0. The position at time 0 was 0. And so I'm just trying to justify that one way to think about this now moving forward is exactly in what we're seeing right here. To do an antiderivative of a velocity function, or I'm sorry, to do a definite integral of a velocity function from 0 to 10, we can do the antiderivative of that velocity function, which is position, and evaluate the position at the upper limit, and then subtract the position evaluated at the lower limit. This is precisely what's happening with the fundamental theorem of calculus, or what I should say is the main result from the fundamental theorem of calculus. So moving forward, I'm not going to really talk about the proofs much more, but I am going to apply this over and over and over again. So let's do that in these examples right here. And these examples are probably the most important type of thing that you're walking away from this section with, is the ability to solve these things. So according to the fundamental theorem of calculus, I can take the antiderivative of 2x minus 1, which would be 2 times x squared over 2 minus x, and typically you would have a plus c. And then this is what I do. I draw a vertical line, and I'm saying I'm going to evaluate my upper limit in, and then subtract what I get when I plug my lower limit in. But one thing I want you to notice before we even do that, if I plug in 2 here, and then I subtract what I get when I plug in -1, can you see that the c is going to cancel out? You're going to end up with a c minus a c. So as a result, when we do definite integrals, we actually never need the c. So my work would literally look like this. I would do my antiderivative, and then it's going to be, and I could simplify that a little bit, I'm just going to plug in my upper limit, so this becomes 2 squared minus 2, and then I'm going to subtract what I get when I plug in my lower limit, -1 squared minus -1. And so my final answer here is 4 minus 2, so that's 2, minus, this will be 1 minus a -1, so that becomes 1 plus 1, or 2 minus 2, and we get an answer of just 0 here. So that means that the net area bounded by this function in the x-axis between -1 and 2 is equal to 0. And I'm going to show you, after I go through these examples at the end of this video, how you can check all of these answers. Okay, so this problem right here, to evaluate this definite integral, do the antiderivative, and by the way, this is x to the 1/2. So I can do, let's add 1 to 1/2, so that's going to be 3/2. So the coefficient in front, 2/3 x to the 3/2. Then we're going to evaluate from the upper limit, and we're going to subtract what we get when we plug in the lower limit. So this will be 2/3 times 4 raised to the 3/2 minus 2/3 times 1 to the 3/2. And a little bit of evaluation here. We're doing the square root of 4. That's 2. 2 cubed is 8. 8 times 2/3, 16/3. So we get 16/3 minus, this will just be 1 to any power is 1, so this will be just minus 2/3. Final answer, 14/3. Okay? Let's go on to number 3. What function has secant squared of x as its derivative? Well, the function that has secant squared x as its derivative is tangent of x. So we're going to do tangent of x, and then I draw this vertical line to indicate I've already done my antiderivative, but now I need to plug in that upper limit, and then I'll subtract what I get when I plug in the lower. So tan of pi over 4 minus the tan of 0. The tan of pi over 4 is 1, and the tangent of 0 is 0, so my answer here is just 1. We've dealt with absolute value problems before, and whenever we have, I've always suggested that you graph these. And you probably know what this looks like, and I would suggest just answering this question by hand then, because otherwise we have to actually write that absolute value function as a piecewise equation. I think that's too much work. So I'm just going to visualize this function. X minus 2 is going to look like this. It's shifted right 2. And if I'm doing the net area bounded by that function in the x-axis from 0 to 3, then I'm actually looking for this area as well as this area. And that's crossing that y-axis right at 2 there. And so I can just fall back on my definition of area here, or not necessarily my definition of area, my geometric formulas for finding area in order to find this net area, because again, that's what this definite integral means. And so this question is an easier question to answer by going back to what we did in section 5.3. Simply look at this and say, oh, that's 2 times 2. Let's take half of that, because the area of a triangle is half of base times height. So we're going to have 2, and then this would be 1 by 1, I believe, because if you plug 3 into that function, the height would be 1 right there. So if that height is 1 and that base is 1, then the area here ends up being 1/2. So we end up with an area of 2 plus an area of 1/2 for a grand total of 2.5. And so my answer to this question, 2.5, or you could just write that as 5/2. In general, though, you're going to want to follow the rule where you do the antiderivative, plug in the upper limit, subtract what you get when you plug in the lower limit. But look out for these special case problems where you still can rely on your geometric formulas and things like that. Okay, antiderivative, let's do it. It's going to be x squared over 2, and then the antiderivative of 5 to the x. You might remember that this antiderivative would be 5 to the x divided by the natural log of 5. We're going to plug in 3 and then subtract what we get when we plug in 0. So this is going to give me 3 squared is 9, so we're going to have 9/2 minus 5 cubed over the natural log of 5, and then minus 0 squared over 2 minus 5 to the 0 over the natural log of 5. And this is not the cleanest answer here. We're going to get 9/2 minus 125 over the ln of 5. This goes away, and then we're going to be adding 1 over the ln of 5. So the best answer here would be 9/2 minus 124 over the ln of 5. But one thing that you can do in all of these is you can always check your answer. For instance, if we go back to, let's go back to, I guess, number 1. So you can plug your function into the y equals menu, and our function here that we're integrating is 2x minus 1. And then you would say, let's just go take a look at the graph real quick. Pretty basic looking line. And we want the net area, the definite integral, evaluated between -1 and 2. So you could press second trace to go into that calc menu, and it's number 7. So it doesn't look like a definite integral, but it actually is. And our lower limit is -1, upper limit is 2, and it shades the area and then evaluates that area for you. So it says that that net area is equal to 0. Or if we wanted to do another one, let's just check our second one. For instance, we had the square root of x as the integrand. So if you have the square root of x, and we want to evaluate this integral from 1 to 4, we know that's going to be a positive amount. So the definite integral from 1 to 4 is going to be the net area bounded by the function in the x-axis from 1 to 4. So you see the answer is 4 2/3, and that's exactly what 14/3 is. So try to get used to this pattern, this process. You're going to get used to it just because you're going to practice it a lot now. You're going to see it a lot in Calc 2. But then, be able to check your work through these other methods as well, but like using the calculator and things like that. Okay, so in the next video, I'll just keep going with the notes.